this is an experiment, because I'm going to be talking about the foundations of computational mathematics. But the idea is that this should be hopefully interesting to essentially anybody interested in math who owns a computer. And of course, I'm going to emphasize the important links to sort of the core theme of this workshop. So this is joint work with Jonathan Benartzi, Ben Jennings, Olavin Evelina, and Marcus Seidel. And I'm going to start this talk by asking a simple question. Classical complexity theory can essentially be divided into two categories. The first one is the set of problems that can solve in finite time. So the famous P versus NP, the whole polynomial hierarchy. This is the core part of classical computer science. All great. We don't need to spend an awful lot of time investing in and telling why this is important. It holds one of the most important problems in mathematics. The interesting thing is that this class, although highly interesting, does not have so much to say in scientific computing. Even just computing eigenvalues of a matrix, I have a finite amount of input, but I can't solve that in finite time. The problem in scientific computing is actually over the, for example. This hope for is essentially to have some kind of approximation. At least I can form, say, a sequence of approximations, and I can compute that approximation in finite time, and that approximation converges to what I want to get, right? The key question that I would like to ask is, do most computational if there's some bizarre that I'm asking, do most computational problems fall into these classes? Around and if I have a polynomial of degree 5 and I can see the polynomial coefficients, can I compute that polynomial by using finitely many arithmetic operations and you all know this, right? What I want to emphasize is that this is the computability problem. I have a very well-defined problem. I can see the polynomial coefficients. Asking that I can compute the zeros of this polynomial by using finitely many arithmetic operations and radicals. No, I can't do that. What if I'm allowed to pass to a limit? And by that I mean I could essentially form a sequence of approximations. Each one of these approximations I use finitely many arithmetic operation radicals, and that those approximations should converge to the true solution. Can I do it then? Yes, I can. What if I take radicals? What if I ask for a halting parameter? I ask for an epsilon. And the algorithm should halt and spit out a solution that's guaranteed to be within the true solution. That should work. This is wrong. Now with a list of problems that I think is sort of a core problem. The first one on the list is the computational spectral problem. I'm interested in computing the spectral operator. But in reality, I allow it to be simply because most problems in mathematical. So in this case, I assume that I have coordinates the computer can read, and I simply ask, can I compute this spectrum by using arithmetic operations and radicals? Then I can weigh the radicals as well. But now let's keep it. Another problem, classic solve the same coordinates. Just resist an algorithm, I can compute the solution. Third one on the list, different from the other ones, in the fact that here I have a specific Schrödinger. I don't have the coordinates of this. I have the potential function. That's what I can see. I can sample the potential function. It's the potential function that defines the spectrum. I'm asking simply, can I take arithmetic operation and radicals of those and using limits, obviously, recover the spectrum. This is very different from here. There's a potential infinite, very uncountable amount of information I'm sampling from. The question is, can you do it? The fourth one on the list is I have a polynomial, and this is quite different from I would like now to compute a root of the polynomial, but there's no radical. But I'm also just performing a rational map from polynomial coefficients, so that the rational map iterates on complex numbers and hopefully give me a root. There exists an algorithm that can do this. Now, here is a good old problem that we all know very well. I could also ask this if I have something completely implementational. And I could just take optimization problems here. Now, what about this here? In this case here, I suppose I fix t. Here, form the transform. I have my measurements, and I can sample those measurements, and I would like to solve this TV problem. And I'm simply asking radical. Seventh one on the list is a famous PDE. It's simply the time-dependent Schrödinger operator. And I'm asking, yeah, I could have PDE infinite boundary here, and that makes it very different from a lot of things. And the question can sample the starting and the potential function, and the question is, can I actually? So I'm going to start with a problem. So Steve, so I like to take and create a rational map. It should iterate complex from several. First is there exists an algorithm that can do this. It's much, much closer to essentially the foundation computers that were established in the 30s by Turing, Go, and so on and so forth. Also, essentially, Smith, and he doesn't really with this is that this is the start of the problem. And the outcome in the journal. Yeah, you can't formulate the that was one of that's male set. So you can't formulate small 7. Anyway, so this has a solution. Is no. Pieces when he paper. I must admit that the actually more sophisticated. I highly this is actually all paper. And in '89, he published a paper with Peter Doyle. Was when they were both. get an output, can be used as an input, which is to say that used input in is the gospel of scientific computing. Are essentially on the first one level. So now what about to the spectrum, only finite. But spectral Brian Davis should actually though there's been a it could, there's we have to be careful. Now the thing about that spoiler, if there was something going on. At that point, it happens everywhere in computational context. Right. What was in small now. Completely, these are the ones that we would like to compute with. I can't feed that into my computer, so I need a set of what we call a complex valued function, and I call this set of the valuation. The ones that are going to get in a yes. Whatever you want. A very simple example would be this. Okay, here these would be the complex subsets. Information J that simply gives me the matrix coordinates. And then the question is, what can I call this? Problem. So I call all these things here the problem function with its domain, taking values in my metric space, and these function, the set of functions that I can essentially read my computational problem. This is called the problem. And I'm going to solve that, and I need to solve that in some kind of on. So the first thing that I need is I need to make sure that I can only work with a finite subset of these. I can only take a subset. I'm going to work with a digital computer. Don't have to. But the finite set of information can be adaptive. It can depend on the input. Then the action that I have of my algorithm can only act on a string of numbers. So this is a. But now I need a condition, a sort of a consistency condition. So if I have now f is in this evaluation set of my algorithm with an a, if I compare that, the input of my a, with another input, b, and it's the same, well, then I actually have to have the same amount of information. So this is to make sure that this, I can't have while. Any algorithm cursive don't have while. Is wider than that. Anyway. So keep in mind that we want to have a setup that allows for things that you need several limits to compute. And for that, we need what we call a tower of algorithms. A tower of algorithms is simply a bunch of different functions indexed from n1 to nk. And I don't actually need to have any restrictions on these guys, except for this one here. This is the lowest one in the hierarchy. And that has to be a general algorithm. I haven't said yet what it can do. I'm going to do that later on, because I want this to be completely free of any axioms of what the computer can. Only about how it can read. That's the whole point. Yes, that's the key thing. And then I can essentially approximate through several limits what I would like to compute by passing here n1 and then n2 and so all the way up to my xi, which is what I'm interested in computing. Now we define this abstract complexity by saying that solvability complexity index of some problem but here I need, here what I've done, I haven't specified this yet because it said it has to be the SCI with respect to a tower of algorithms of type alpha. Now, in a second. No tower exists, then the index your algorithm halts and it spits out the solution. Zero. There's one arithmetic chapter. That the lowest hierarchy, the general algorithm, can do only arithmetic operation. A general algorithm can do whatever you want. Only restrictions on how it's made. It says that you can only do arithmetic operations. A radical power, arithmetic operations, and so interesting. It's not new, it's really to see if I was able to idea. My moment is the set of 4x4 matrices. And is spectral map, like a computer. Okay. Good. Final minute. You can plug that into okay. No. So this is a good point. The other one Well, you can actually do this with one limit. So the point is that the insolvability of the quintic is actually an index problem. It just asks, does this have index 0 or not? And then finding an algorithm to show that it is actually index 1 is correctly, can I design an algorithm that can do this? So what I'm going to do now is I'm going to show you several examples of where you see the index. And I'm going to show that relate this to other subjects, not just spectral problems. But before I do that, I'm just going to define what's called the N pseudospectrum, because I'm going to make statements about that, and I'm not going to spend a lot of time justifying why this is important. Spectral theorists do like other things than just the spectrum. So this is essentially, you take the spectrum, and then you have essentially a set outside the spectrum, and depending on this quantity here, when this is bigger than epsilon, and the point here is that as n grows large, this shrinks to the epsilon neighborhood. That's why this is a normal case. Anyway, so what is the solvability complexity index of the spectral problem? It would have been a little dull if it was 1, right? Because now I've sort of hyped this up. So if it turned out to be 1, it wouldn't have been that interesting. So is it then 2 or is it 3? And this is actually 3. And I'll tell you what the theorem essentially says. So this here means an arithmetic tower. And what that means is that there does exist a way of computing the spectrum with 3 limits if I'm allowing arithmetic operations. I don't need radicals for this. But what it also says is that there does not exist any other algorithm that can do this, that uses arithmetic operations, that can compute the spectrum. But there's more to it. This G here stands for a general tower. There is no restrictions on the operations I could use. And it's still 3. And that means that I can throw the kitchen sink at this problem, and I won't be able to essentially improve on it. Even if there existed an algorithm that could compute the spectrum of an n by n matrix in finitely many arithmetic operations, I still would not be able to improve on this. I could even take this to be a smaller set where the matrix has only zeros and ones. And in that case, it's still 3. And what that tells us is that regardless of the axioms, we still see this variable. Easier. We'll have if I add more structure to it, then I can also lower the index. And this is the key part. What the index tells you is that the big problem is very difficult. And to be able to lower the index, you need extra information in. The algorithm needs to take that information. And not only that, it is impossible for any computer to learn that on its own. That is something that has to go into the algorithm. So in this case here, I have self-adjointness, and then I can lower the index, but I still have this lower bound. You can sum up essentially all the work of McMullen on polynomials. So in this case here, you use what we now call a Doyle-McMullen tower. It's not a radical tower, and it's not an arithmetic tower. It's essentially stacking these rational maps on top of each other. But you can formulate this as an index problem. So for the degree of polynomial less than or equal to 3, the index is 1. There does exist rational map to do this. It's not Newton's method for the cubic. In the case of 4 and 5, the index is either 2 or 3. To be fair to them, they actually didn't want sharpness. They just asked, does there exist a finite tower to do this, which they answered. And if you actually go through the proof, you see that the upper bound is 3, but we don't know if it's 2 or 3. In the case of a 6th-degree polynomial, it is any that can do it. So what does this teach us? Well, it says essentially that there must be a hierarchy here. Not all problems can be equally difficult, right? There must be a classification hierarchy on different, essentially, difficulties of the different computational problems. And this is essentially the key to the Solvability Complexity Index hierarchy. So the SCI hierarchy is as follows. I will have to define a type of tower. That means whatever my computer can do. Radicals, arithmetic operations, whatever. And then delta 0 is a set of problems that has index 0. That means that you can solve them in finite time. Delta m plus 1 is the set of problems for which the index is less than or equal to m. And then delta 1 is the one where you need one limit, but you do have error control. And this is very important. So when the algorithm halts, you know that you're within 2 to the n. So that means that you have delta 0, finite time. Delta 1 is the set of problems for which you can compute in one limit, but you have control. Delta make this you will just collect the matrix elements, right? And you will never know if you have everything, but the ones that you actually have, you know that is in the spectrum. The other one here is the opposite. It says that the true solution is within what you have computed. So suppose that the solution to your problem was, say, the element 1. This is of interest in particular theory because in quantum mechanics you're interested in knowing, for example, is the spectrum have a... And this can also be made more general into higher order classes, these sigma n's, m plus 1, and pi. I'm just going to mention before I go into the actual problems what I mean by a basic algorithm. So finally leads me. So now, hopefully we're done with the dry part. So now we can always. Here are the questions. So if you have a problem that you would like to compute, where in the SCI hierarchy is that problem? And if somebody's been able to figure out what the classification, the question is, the algorithm that you're using, is that a basic algorithm? For example, computing the n matrix in the hierarchy. Now, this question here is actually one of the main questions left in numerical linear algebra. It is not known if this is a basic algorithm. It's not even known if the QR algorithm is globally convergent. This is... Sorry. So it's simply the ones that gives you the right classification in the hierarchy. So if your problem is sigma 1, then the algorithm can be the algorithm basic, right? And nobody knows. This is very delicate. There's almost a year algorithm. What that so that would, you know, this delta 1 class you want. You have error control. Awesome, right? It's going to be the point is that even this thing here is, you know, and you can make a lot of statements like this for problems. For example, here, have index 2. You can what do you throw? Paper by Thomas Schirmer and Charlie Gröcknick, but it could be that there's other ones. I have no idea. But the lower bound is very important. But the key thing now is that I may not be interested in the general problem. I'm interested in my specific problem. Where in the hierarchy is my specific problem? Do I have a basic algorithm? Right? All right, where do you see the SCI hierarchy? So nobody can really claim that, you know, they invented the index. The index has been there since, well, early. And it shows up in a lot of different areas of mathematics. So I've mentioned this before. The insolvability of the quintic is a classification problem. It just asks, is the problem delta 0 or not? It is not delta 0, right? That's the insolvability of the quintic. Getting it to be delta 1 is somebody cooking up an algorithm that can do it, right? It could have been delta 49 for all we knew, but it was certainly bigger than delta 0. Turing, the halting problem, famous halting problem, what Turing showed was that this is not delta 1. It is sigma. And then with this comes also the arithmetical hierarchy. If you were lucky enough to recursion theory and logic for grad school, I wasn't. You recognize this here as a very special case of the SCI hierarchy. So this is what the logicians worked on through the 50s and the 40s and the 50s, where essentially this here is at the lowest level, or not the lowest, it's in the sigma 1 class. So this is actually a very specific case of the SCI hierarchy, and these fun delta notation and the pi and the sigma come from the arithmetical hierarchy. The insolvability of the quintic using rational map, as I mentioned, is an index problem. Computability of real numbers, you might find this interesting. For any k, any integer k, there exists a set of real numbers for which you can only compute with k limits, not k minus 1. And spectral problems, we discussed that. I mentioned inverse problems, and then obviously optimization problems, and PDEs, and essentially wherever you see computational mathematics. And this brings me back to the list. So I mentioned that there's one problem here on that list which is impossible. I've revealed the solution. This is impossible, which is essentially a classification problem. This is the one which is completely unknown. It's fascinating because it's more than 80 years since Schrödinger got a Nobel Prize, but I don't know how to solve this problem, and nobody else does. What about the things that we care about here? What is the index, or where does this belong in the hierarchy? I don't know. I can show that computing, pardon me? At least 2, but I don't know what it is. And it will depend on where this is in the hierarchy in the finite dimensional case. If I ask this problem in the finite dimensional, it's not clear to me that this is delta 1. But then again, I'm not an expert in optimization. So what is it? If it's not delta 1, well, then I'm interested in knowing which matrices from which observations it is delta 1. Is this related to some kind of subsampling? If I'm going to cook up theory on doing compressed fencing, and I can show that log n I can recover, but it turns out I can actually not compute this with error control, well, then I would like to know it. I don't know. What about this TV optimization problem? I fix my t, it's the Fourier transform. Where is it in the hierarchy? I don't know. Where is Gabriel's problem in the hierarchy? I don't know. And then, finally, yes, so the point is that first, I'm doing something which is interdimensional, right? So I throw in a discretization, and then I need to solve that one. So the question, if I can collapse several limits into one, awesome. That would be great. But you need to control to be able to know that. So one of reasons why I thought this was very interesting. I was a thesis examiner on an imaging thesis, and there was a lot of beautiful analysis in the interdimensional case, and they did Murex with an algorithm. And just expert at all. I'm just saying. So what about this one here? I don't even if there exists an algorithm that solves this. Do is put official boundary conditions, boundary conditions. This is the first time in my career I actually started working heavily on PDEs. It's very interesting. And we'll hopefully the point then has to some out right? How am I doing on time? Ah, I can take figures. Okay, so I was hoping to announce, the grand thing I can solve, sure, but we're getting somewhere with it. So, your problem is substantial and so it's still pretty weak, but I don't claim that I've solved it. It's delta limits. You know if it's not I'm my right hand. At least we can to the discrete case. The classification of the discrete Schrödinger operator is so the neat thing is that you will not all right. So the initial classical the take-home message before is not collapse regardless of if on a blue machine. Interesting thing is they work in delta zero. It has potentially a very rich hierarchy as well, but they need to solve P versus NP before they can actually see which P is equal to they can start right. Just the interesting thing on top of it is P get the problems. So I haven't put here, there should be an alpha. So P and that decision. This is what I'm saying. It depends on what you're allowed to do. So that's this. Which one? Oh, this one here? Oh, okay, so from computation 1 and if I just add it on my computer, then in correct. But it's never the case. Throw in whatever you want. SCI is absolutely in line. Tons of problems. So PDEs, optimization problems, whatever you want. So here is the thing. Please help out. Finally, picture. So one may ask, these actually so here's a very simple example. I'm going to choose multiple. That's exactly what the spectrum is. This will give me an infinite matrix. Here's the spectrum. And here's what I actually do. But the algorithm will require 3 different indices. And do something. Isn't right? We're never going to have universal algorithms. We're going to have a whole wide range of different algorithms for the different specific problems and making sure that they're basic. I want to show you a slide which I think is kind of neat. This is the almost Matthew operator from the famous 10 Martini problem. And this is a computation which shows you a Hofstadter butterfly. And this is done with basic algorithm. So what you see here is guaranteed, well, in this case, within 2 digits, to actually be in the spectrum, because this is a basic algorithm. And this problem here is sigma 1. If you compute this with, say, the finite section method, and this is not a new thing because that the finite section method gives you a lot of garbage is shown here, and that's not a new thing. And this is not even a basic algorithm. So is this. However, I just want to say, still a lot more to do, because this isn't the general case. What if I have even more assumptions on my potential? Can I then actually lower that? So I end up almost each time I do classification asking again, can I do better? And then, can you lower that in the hierarchy? So with that, I thank you for your attention and sort of leave with the take home. Thank you. And delicate thing. Getting from 1 to 2, you can. And then you trick the algorithm by coming up with examples. To limit the trick that we're using is essentially with these I would say it very well. But this is so often, so the paper out actually doesn't even you know, I have very good question, but I can't answer. But indeed, very good point. Yes. Yeah. That's not the or it's not. I have no idea. Still, you can ask all these issues here with stable things. Does there exist stable algorithms? But the issue that the computer scientists, even more the stable algorithm that they solve. Just ones are one. Oh, totally. Yeah, absolutely. But the problem is, like for example, the spectral problem. You're interested in computing something, and you don't know. No idea. So for me to essentially get the delta, that's going to be something which depends on a finite input. My potential, it is highly unlikely. You can cover thing and say, here is delta 1. This is delta 1. So just begin.